In addition to his laws of motion, Isaac Newton also worked out how planetary bodies orbit each other in the solar system, and he deduced his universal law of gravitation. When used in combination, Newton's laws of motion and his law of gravitation allowed, for the first time, the mathematical prediction of the orbits of the planets and moons that he could see in the solar system. We've already seen Newton's laws of motion in a previous video, so let's now cover the law of gravitation and how Newton developed this idea. In the late 16th century, the Danish astronomer Tycho Brahe had carried out meticulous observations on the motions of heavenly bodies over a 15-year period. Brahe produced amazingly detailed and precise measurements. He noted the positions of over 1,000 stars, and he also recorded the movements of the planets and comets against the background of stars. It is amazing to think that Brahe did all of this without the use of a telescope, which would not be invented until a few years after his death. Brahe's observations were published after his death and were taken up by the German astronomer Johannes Kepler. Kepler had briefly worked with Brahe just before Brahe's death, and so Kepler was aware of the data which had been collected. Kepler used Brahe's measurements to deduce how planets actually move, and he came up with some relationships for the movement of the planets, and these became known as Kepler's laws of planetary motion. Kepler's three laws can be shown like this. The first law simply states that the planets move in ellipses around the Sun. Kepler did not prove this mathematically, but as in so many cases, Newton worked this out as part of his calculations in Principia. Kepler's second law says that a planet sweeps out equal areas in equal times, which is also another way of stating that the planet speeds up as it gets closer to the Sun and slows down when farther away. And the third law states how long an orbit takes in relation to the size of the orbital ellipse. Kepler's laws of planetary motion were really observations for how planets move. They were not precise equations of motion. Using Brahe's and Kepler's data, Newton developed his own ideas of how orbiting bodies move and managed to work out a mathematical framework to describe planetary motion. And included in this was Newton's law of gravitation. Newton's work mathematically confirmed Kepler's deductions, like the fact that planets move in elliptical orbits. But it also went much further than anyone had done before. Not only did Newton's theories explain what could be seen in the solar system now, but for the first time the equations could be used to predict what would happen to the planets and comets in the future. And this was revolutionary. In many ways, this was the birth of the modern scientific method, where we observe something, propose a theory to describe the observations, and then test the theory by making predictions and checking the outcomes. Exactly what Newton did in the 17th century. Before going into Newton's law of gravitation, let's just say a few things about orbits first. Imagine there are two bodies, for example, the Earth and the Sun. Normally we just say that the Earth orbits the Sun, but in reality, the Earth and the Sun are actually orbiting each other around a common centre of mass. And this common centre of mass is known as the barycenter. In the Earth-Sun case, the barycenter is very close to the centre of the Sun, only around 500 kilometres or so from the centre of the Sun, in fact. And this is because the Sun is so much more massive than the Earth. So for all practical purposes, we can simply assume that the Earth orbits around the centre of the Sun because the difference from the barycenter is so negligible. In the case of two bodies which have equal mass, then their barycenter would be exactly halfway between the two, and so the two would orbit around a point in space equidistant from each body. So even though two bodies will orbit around each other at their common barycenter, in cases like the Earth and the Sun, we can simply just think of the Earth moving around the Sun because the difference from the barycenter is negligible. This is also a typical example of something we do a lot in physics, which is to simplify a problem to remove unnecessary complications such that the core principle can be looked at. We might add the complications back in later once we've worked things out, but it is often much clearer to simplify the problems, like just assuming that the Earth orbits the Sun. Now to Newton's Universal Law of Gravitation. So let's assume that a body is orbiting around another object, in this case the Earth and the Sun. But of course these two bodies could be anything as long as they are orbiting around each other. We can say that the larger body, the Sun, has a mass capital M, and the small body, Earth, has a mass small m, and r is the distance between their centres. Newton's law of gravitation states that the gravitational force between the two bodies is proportional to the product of their masses and inversely proportional to the square of the distance between them. We can write this as an equation, F equals gmm over r squared. And g is the constant of proportionality known as the universal gravitational constant. G is in fact a fundamental constant of the universe and also appears in Einstein's general theory of relativity. This simple equation is actually very powerful, and we can say a few things about it. We note that the force of gravity, which we can call Fg, is inversely proportional to the square of the distance r, and this is known as the inverse square law. This law applies not just to gravity, but also to light, electrical charge, radiation of any kind, in fact, anything which has field lines spreading out spherically from a point. We can visualize the inverse square law like this. In this example, if we say that the strength of a source is something called S at the center of the Earth, this could be gravity, then on the Earth's surface, the strength of the source will have reduced because the source is radiating out in all directions, and so its strength per unit area is diluted. As you go further away, it becomes weaker. We know that the surface area of a sphere of radius r is given by 4 pi r squared, and so the source strength per unit area at the surface of the Earth will just be given by S divided by 4 pi r squared. So then we have the source intensity at the surface. We can call that I, for example, and then every time we go a distance further away, this intensity reduces in relation to r squared. Because the area is increasing, the strength per unit area decreases accordingly. So at a distance 2r from the centre, the area is 4 times larger, and so the intensity is 1/4. And at a distance 3r, the area is 9 times larger, and so the intensity is 1/9. Another feature of Newton's law of gravitation is that it also obeys Newton's third law of motion. So if the Sun exerts a force Fg on the Earth also exerts an equal and opposite force Fg on the Sun. So now, in addition to Newton's 3 laws of motion, we also have Newton's law of gravitation. And Newton used these laws to work out how orbits work, as we shall see in later videos. I hope you found this video interesting, and until next time, keep thinking physics.